Okay, in this one we're going to work 10.5. This asks us to draw Lewis dot structures for three different compounds. Drawing Lewis dot structures for molecules is one of the really key skills for Chapter 10. In terms of preparing for your last exam here and the final exam, having the ability to draw these Lewis dot structures is absolutely crucial. You can see problems on your homework and also your exams that directly deal with this concept, where you're directly asked to draw Lewis dot structures. Believe it or not, you're also potentially going to see follow-up questions based on something called the Vsepr theory, which predicts shapes of molecules. And unfortunately, if you're going to be able to do that successfully, the first step involves getting a good Lewis dot structure. So this is a really important topic, and I want you all to practice this, okay? It follows a very specific protocol for each problem for the most part. So you just got to practice it, I think, to master it and get good enough at it, all right? So we have three different compounds. The first one is SiF4. Let's talk about what we need to do to come about a Lewis dot structure for each of these compounds. Now the first step in coming up with a Lewis dot structure is always the same, okay? It's count valence electrons. The valence electrons are our ingredients for our chemical bonds, okay? That's where the chemical bonding occurs, in those valence electrons, those outermost shell electrons. So we make a count of them to see what we've got to work with, okay? Now how do we do that? Well, for each element, really each atom, is probably a better description, we write the contribution for that atom. So you got to find the elements on the periodic table. Silicon is right below carbon. Silicon's atomic number 14. So since it's in group 4A, it tells us that we've got 4 valence electrons, just like carbon. Okay. Now each fluorine, we know that fluorine is a halogen, it's over further to the right, between oxygen and neon on the periodic table. And since it's in group 7A, each atom of fluorine that's in the compound contributes 7. We've got 4 atoms, so we're going to have to do 7 4 times. So again, you have to add up the atoms contribution, okay? So it looks like what? This is 28 plus 4, 32 electrons. That's what we've got as our ingredients to build our chemical bonds. It's all the electrons we can use, and we have to use 32. We cannot lose any, all right? So, what's the next step? The next step is to place the least electronegative atom in the center. Now, in this case, that's my silicon. Because fluorine's very electronegative. The most electronegative element, fluorine, as a consequence, is extremely unlikely to ever be a central atom, okay? But silicon will work as our central atom, and it's very frequently a central atom, just like carbon. Carbon's basically always, when you see carbon in a structure, it's basically always a central atom. So we can put silicon at the center, and then we can bond other things to it. So kind of point C here. Distribute other atoms around central atoms. Form single bonds. So after you figure out what the least electronegative atom is, you put that in the center, and then you distribute the other atoms around the central atom. Sort of symmetrically, okay? And you establish single bonds. Now, remember, a single bond involves the sharing of 2 electrons. So I could write that, or these electrons are shared between the silicon and the fluorine in each case. Now, they don't have to be shared equally, but they're just shared. Alternatively, it's probably more common, instead of writing these dots, to write a line. And that represents the single bond. So the line basically is equivalent to this pair of dots. Each line represents 2 electrons. It's a chemical bond. Again, electrons need not be shared equally, but they are shared to some certain extent. Okay? All right, now the last step, or one of the last steps here, as we proceed through drawing our Lewis dot structure, is to distribute the remaining electrons to complete octets. So we want to try to complete our octets. Now, what is this completing octets? Well, remember, we talked about one thing that drives chemical bonding is atoms trying to get that full p shell electron or complete their octet. That's both the s and the p, atomic orbitals, if you want to think about it that way. Okay, but they want to, except for hydrogen. Hydrogen only needs 2 electrons, but other elements like to have 8 of these valence electrons that they're participating in bonding with. Okay, so as I look at the structure, the central silicon is really kind of golden, probably, because it's got 2, 4, 6, 8. Each of these lines represent 2. And since it's got 4 bonds, that's 8 electrons that this guy is participating in bonding with, and that's good. It complies with this octet rule, right? But as it's written right now, these fluorines only have the bonding pair, which is 2. And that's not so good for fluorine, because fluorine loves to have electrons, right? Highly electronegative. It's not going to be happy with only 2. So, we're going to have to complete the octets for fluorine. Now notice what I did in each case is I drew 1, 2, 3, 4, 5, 6 dots around each fluorine. 6 dots plus these 2 make 8 electrons. Each dot is representative of an electron. Now, these dots come in pairs of 2 when you add them to the structure. And chemists like to call them lone pairs. Lone pairs here, 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 and here. Alternatively, the ones that are involved in a bond, you might call those bonding pairs. Electrons, they come in pairs in these structures, okay? Now, the last thing I need to do is evaluate the success of my structure, or whether or not it could really exist as I have it written. There are things that are good about it. I know that, right? Because each fluorine now has 8 electrons associated with it, 6 lone pairs, 2 in the bonding pairs, or 3 sets of lone pairs, which is 6 electrons, and then 2 more in the bonding pairs. That makes 8. There's 8, 8, 8. My silicon's happy. It's got an octet. So from a chemical perspective, this looks pretty good. But there could be a problem. I basically kind of made this up, not paying any attention to how many electrons I actually had to use. What if, when I was drawing my structure, I've used the wrong quantity? Maybe I used too many or too few. That would violate my ingredient list, okay? And that's not going to work. So my last step is to assess whether or not what I've drawn is possible based upon the ingredients that I've got, these 32 electrons. So the way to do that is you add up the electrons that you used and see if it matches what you've got. All right? Pretty simple. So as I'm looking at this, I see, okay, well, I've got 1, 2, 3, 4, 5, 6 lone pair electrons for each fluorine. So I've got 4 fluorines. If I multiply 4 times 6, that's 24. Just these lone pairs on the fluorine. Now I also need to add back in my bonding pairs, right? So there's 2 here, 4, 6, 8. So if I add back in the electrons that are involved in bonding, there's 8 more, and that makes 32 electrons. Now fortunately, that matches, I've used what I had, right, which is a very good thing because that's a requirement for my Lewis dot structure. So, what that I would say about this structure, I think that what I've come up with is a perfectly valid Lewis dot structure for this compound SiF4. I'm happy with it, and I'm done with the problem. All right, so this is your thought process and the procedure. Okay, let's try it again. SeCl2. Now, what's our first step? Think back to the list. Count valence electrons. See what you're working with. You got to locate the elements on the periodic table. Se is a 6A main group element, which means it's got 6 electrons. I've got 2 copies of chlorine. Chlorine's right below fluorine on the periodic table. So it's got a consistent number of valence electrons here. That's 7. Right? So let's see what we got. 7 is 14, plus 6 is 20. I've got 20 valence electrons available to me now to make my bonds and hold this thing together. Alright, so let's think about this then. My next step, figuring out what's in the center. Now chlorine's up near fluorine, right? Chlorine's right below fluorine. It's reasonably electronegative. Remember, we want the least electronegative atom in the center, whether we want the lowest main group number. And here, in this case, I am pretty confident that's going to be my Se. That's going to go in the center. I'm going to form bonds to chlorine. I'm going to distribute my chlorines sort of symmetrically around the central atom. And now I'm going to start to see how the bonding works in this molecule. Now I've already drawn in one line here and one line here because I've got to hold the molecule together, so I've got to have at least a single bond, okay? Remember, that's 2 electrons and 2 electrons. We'll get back to that here in a second. Now what else would be my next step? Well, after I hold the molecule together by forming these single bonds, I complete my octets. So I'd start by doing 6 electrons here to chlorine, and 6 electrons here to this chlorine. I like to do the element of highest electronegativity first, because those are the ones that really like to have those electrons. Okay, so 6 plus 2 is 8 for that chlorine. 6 plus 2 is 8 for that chlorine. Now the central atom's only got 4 right now, so I need to add 4 more dots here. So I keep adding lone pairs to complete the octets, basically. Okay, that's going to be my strategy. Alright, so after I propose this structure, I have to check for its validity to see if, in fact, I've used the correct number of electrons. If I have not, I have to revise my model. Okay, so let's see where we're at. We got 6 lone pairs here, lone pair electrons here, 6 lone pair electrons over here. I've got 4 in my central atom. I've got 2 involved in this bond, and I've got 2 more involved in this bond. So this is my inventory, right? So how many total electrons have I used? It looks like this makes 10, 12, 14. I think I'm right at 20, right? So this structure requires 20 electrons, or uses 20. I, in fact, had 20 to use, which means that it's good, it's golden, right? If you find a discrepancy between what you used and what you have to make an important modification. I think we'll see an example of that later, okay? Once we get experience with it. All right, but nonetheless, that would be a successful answer. All right, last but not least, we've got this molecule, COF2, okay? All the same exact protocol over and over and over, okay? Carbon 4A group element, it's got 4 valence electrons. Oxygen's got 6. Each fluorine has got 7. We sum the total number of electrons that we have to build our structure, 14, 20, 24. we have 24 electrons that we're allowed to use. Now when you see carbon in a molecule, it's generally always in the center. Okay? So I'm going to start by doing something like this. I'm going to make a little T-shaped molecule. Now, the drawing that I put on my piece of paper really just distributes these atoms somewhat symmetrically around the central atom. Does not mean that this is what the actual geometry of the atom is. Okay? We use the so-called Vsepr theory to help us with that, but right now I'm just trying to figure out how the bonding works in this molecule. So that's kind of what I would start with, the lowest electronegative element or carbon in the center. Distribute the others around it. I have single bonds here, here, and here to hold the thing together. Now I start to complete my octets. So I would do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 24, 26. Uh-oh. So what I just did is I counted the electrons that I've used here, and I found 26 electrons were used. I only had 24. So this is not going to work. Okay, the structure is not correct because it requires 2 more electrons than what I have to use. I need to revise. The way that I revise my structure is by sharing more electrons. Okay? In such a case, if I've used too many and I don't have enough, I just need to share more. And if I share more, I can make it work. Okay? So what immediately caught my attention here was the single bond here to the oxygen and this lone pair of electrons in the central carbon. It's actually a little bit of an unusual structural feature. Okay? Just from experience, I know that oxygen likes to form 2 bonds. Right? If you think about water, for instance. Water has this Lewis dot structure. The oxygen forms 2 bonds, and that's pretty common, as it turns out. Oxygen likes to form 2 bonds. So I could form a double bond, which is a sigma and a pi bond here to the central carbon, sharing another pair, and maybe this would work. Now, on the other hand, carbon likes to form 4 bonds, and almost always does. Fluorine likes to form 1 bond. So by kind of experience or convention, those guys should be pretty happy with this structure. So let's see if it works out. So how many lone pair of electrons do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 lone pair. And then how many bonding electrons do I have? Well, it looks like 2, 4, 6, 8, because I've got 4 bonds now. If I do the math on that, it looks like, in fact, I've used 24 electrons in this structure where I've introduced this double bond right here. I've shared more electrons. So you can see how previously with the extra lone pair and the 1 less bond here, we required 2 more electrons, 26 electrons in that case. By sharing more, now we only require 24 to make this work, and as a result, this would be an acceptable Lewis structure for this molecule, COF2. Alright, so again, I hope that this was useful. We'll probably work on another example of this. I can't stress to you enough how important it's going to be for you to learn the skill of writing these Lewis dot structures. You'll see this kind of all over your graded assignments, so definitely spend some time on it, and if you're struggling, seek out some assistance.